your lesson for 3-5 zeros of polynomial functions. And you'll find as we're moving through the rest of chapter 3, 3-5 and 3-6 are very similar in that they both deal with ways to help you narrow down what the zeros of polynomials are without actually looking at a graphing calculator. So we have our central question here. How are the zeros of a polynomial function related to an equation and graph of the function? So our first example, we want to know what are the zeros of this function, and then we need to graph it. So with our zeros, we have this factored form here, x times x minus 4 times x plus 3. So that's going to give me 3 different zeros. I get 0 by setting the x equal to 0 on the outside. I get 4 by setting the x minus 4 equal to 0 and solving. And then I get negative 3 by setting the x plus 3 equal to 0 and solving. So I know that I can place those values on a graph. Now, if I need to sketch the graph from that information, it's helpful to know whether these zeros are places where my function is going from positive to negative, from negative to positive, or if it's going to stay positive or stay negative. That'll help me figure out what the terms are. And so what I'm actually going to do with that is I'm going to look at a number line here. So there's my 0, there's my negative 3, there's my negative 4, my positive 4. And I want to pick values that are within each of these regions and see if I'm going to get a positive or a negative value when I plug into the original function. So let's use negative 4 as a test point. We can use negative 1, 1, and 5. Because those are the only 3 zeros, the negative 3, 0, and 4, whatever's going on, for example, in between 0 and 4, whatever's going on at 1, that has to be going on for all of the values between 0 and 4. So I'm going to go through and I'm going to plug these into the function. I'm not so much going to be concerned about what the number value is, but I do want to know what sign the value is. So if I plug in negative 4, out in front where the x is, I'm going to get a negative. Negative 4 minus 4 is also going to give me a negative. Negative 4 plus 3 is also going to give me a negative. So when I multiply 3 negatives together, I'm going to get a negative, which means negative y values are below the x-axis. So that means when I am to the left of negative 3, my graph has to be below the x-axis. If I do negative 1, plug in for the x out in front, I get a negative. Plug in for the x with the x minus 4, that's also going to be a negative. Plug in for the x with the x plus 3, that's actually going to be a positive because negative 1 plus 3 is positive 2. And so that's going to be a positive value, which means between negative 3 and 0, I am above the x-axis. And then I'm going to repeat this process for 1. So plug in out in front, I'm going to get a positive. 1 minus 4 is negative. 1 plus 3 is positive. So this one is going to be negative. I guess I'm going to write that the same way I wrote the others. So below. And then when I plug in the 5, I have a positive out in front. 5 minus 4 is a positive. 5 plus 3 is a positive. So I'm going to get a positive value there. And it is above. So if I go through and sketch, I have my negative 3 on the left-hand side. My graph is below. Then I'm going to go above the x-axis between -3 and 0, which means I have to loop up and come back down. Then I'm going to be below from 0 to 4, and then after 4, I'm above again. So your graph would look something like this. We don't actually know how high or how low it goes. This is just going to be enough to give us a rough sketch. So again, these are some helpful hints to aid you in understanding what's actually going on with these questions. So the next thing we're going to talk about is multiplicity. So your multiplicity of a zero, for some polynomial function, it's the number of times its related factor appears in the factored form of the polynomial. So you can have, this would be like, it's sometimes called a repeated root, where you might have the value of -2 appear in your solution twice, or you might have the value of 3 appear 4 times. That is possible. That would be like if you had x minus 3 to the 4th power, you'd have 4 sets of parentheses that were all x minus 3, so that multiplicity would be 4. So we are going to look at this example. It says, how does the multiple 0 affect the graph of the polynomial function? So there's 4 of them here. There's 4 of them. And I do have the solution down below, so I will scroll here in a bit. So x minus 1 is the 0 that we're going to look at, because that's the one that ends up repeating. Although in the top left, it just appears once. In the top right, it appears twice. That would be that blue dot. Do you see how the graph just comes down and touches the x-axis and then goes back up? Then on the bottom left, that 0 of 1, it appears 3 times. Notice how it actually crosses through at 1. And then in the bottom right, the 1 occurs 4 times because it's to the 4th power. Notice how, again, it's a place where the graph touches the x-axis and then goes back up. So you can see here, if you have a multiplicity that is odd, then your 0 is going to be a place where we actually cut through the x-axis, where if it's even, that's actually going to be one of your min or max values, where it's going to touch the x-axis and then continue on its way. So here's the summation of that. When the multiplicity of a 0 is odd, the function's going to cross. When the multiplicity of a 0 is even, the graph has a turning point. Remember, turning points, those are your min and max values. Okay, example 3, what are all the real and complex zeros of the polynomial function shown in the graph to the right? Well, we have an equation. We have a place where it looks like we are crossing. So the real 0 appears to be a 2. Now, I can test this. I can test to make sure that 2 is actually a 0. I could plug it in and make sure that I get back 0. Or the better option would be to check using synthetic division. Because with synthetic division, if 2 is a 0, that means I should get 0 for my remainder. So I'm going to take my coefficients of the function down below, the x cubed plus x squared minus 3x minus 6. So I have a 1 and a 1 and a -3 and a -6. Do my synthetic division. Again, we bring down the 1, multiply and add, multiply and add, multiply and add. So yes, x equals 2 is a 0, and it's actually a real 0. Now the new polynomial that I get back here, remember my highest exponent was 3, I knocked that down by 1. So it's going to be 1x squared plus 3x plus 3. Now to find the complex zeros, I could look to factor, although this is not factor because there are no factors of 3 that would add to 3. The only thing you can get is 4 and -4. So we have to use the quadratic formula to find the remaining zeros. So I have x equals, my a is 1, b is 3, c is 3. So I have negative 3 plus or minus the square root of 3 squared minus 4 times 1 times 3. And that's all over 2 times 1. So I have negative 3 plus or minus the square root of negative 3, because this is 9 minus 12, all over 2. Well, I have to pull the I out of that square root. So we get x equals negative 3 plus or minus I square root of 3 all over 2. And those would be my complex zeros. X equals 2 is my real zero. This is to the third power, which means it has to have 3 zeros. And I believe we're going to talk about that more in 3-6. So I have 1 that's real, and then the 2 that are complex, 1 with the plus, 1 with the minus. And this is something you can use if you can look at the graph, or if they give you a graph where you can easily find one of the zeros. You can always use quadratic formula then on your new polynomial once you do synthetic division to figure out what the other remaining zeros are actually going to be. This is one we're just going to look at and talk about. I'm not going to go through the process of how to solve this. This is in your textbook if you're interested in going through and seeing this. So we have, it says, Acme Innovations makes and sells lamps. Their profit P in hundreds of dollars earned is a function of the number of lamps sold X in thousands. From historical data, they know that the company's profit is modeled by the function shown. What do the zeros of the function tell you about the numbers of lamps that Acme Innovation should produce? So assuming that we're counting by ones here, first of all, we can ignore everything that's over here, because this would be producing negative amounts of lamps, and it's not possible for a company to produce negative amounts of lamps. They could make negative dollars from their production of lamps, maybe because of overhead costs and things like that, but they can't actually produce negative lamps. So if we look at what we have here, we have a 0 at 3, and we have a 0 at 10. Now, if this shows their profit, anytime we are less than 3 in our production, we're going to be making a negative profit. If we're in between 3 and 10, we're going to be in a positive profit, because that's where your graph is above the x-axis. And then if we're greater than 10, we're again going to be making a negative profit. So those zeros are going to tell me that the company should produce between, and this is lamps sold in thousands, between 3 and 10,000 to make a profit. And even further, you would probably want to be about halfway between the 3 and the 10, because that's where it looks like our profit is actually going to peak. You could confirm that 3 and 10 are zeros using synthetic division, but I didn't go through that step here. Okay, example 5. What are the solutions of this big polynomial? Well, we need to get everything on one side first. So I'm going to subtract the 2x cubed, subtract the 5x squared, add the 3x. So I'm going to get x cubed plus 3x squared plus 3x plus 1. At this point, if you recognize that there's some factoring you can do, you can go ahead and factor. You could start picking values out to test to see if something works. So maybe you want to start with like 2 or 4 or 1 or -1. Don't forget about the negative values. But this is something you guys should recognize for this particular question. Notice that the pattern is 1, 3, 3, 1, and my exponents of x start at 3 and then go down to nothing. So this is actually the factorization of x plus 1 cubed. It's not always going to work out all nice and neat. Sometimes you will have to actually go through and do your synthetic division to make sure that you can find one of the solutions here. So this is the factorization here. So whenever I solve this, set it equal to 0, I get x equals -1. This is a triple root. It has multiplicity 3 because I have 3 of the same set of parentheses. So it is going to cross through at -1 rather than being a turning point at -1. In 3-6, we will be looking at ways to narrow down the values to check with this type of question. If you did want to check, you're like, oh, I don't know if that's my value. You could check for your -1. Make sure that you are using the polynomial where everything is on the same side. So 1, 3, 3, 1. And you can see there that would give me x squared plus 2x plus 1, which again would factor into x plus 1 squared. So I'm still going to get those -1s again. Example 6 is the last one we're going to look at in this section. It says, what are the solutions of x cubed minus 16x is less than 0? So we are going to use a graph to sketch this out. We're also going to factor this. So I'm going to set this equal to 0 instead of using the inequalities for right now, just so that we can get an idea of what the factoring would look like. So x cubed minus 16x, I can take an x out of that, and I'm left with x squared minus 16. X squared minus 16 is a difference of squares. Basically, the factors of -16 that would add to 0 are plus and minus 4. So I have x plus 4, x minus 4. So I get 0, -4, and 4 is my solutions. So 4, 0, -4. I can do my number line check if I wanted to on this. So if I look, here's my 0, -4, 4, test -5, I can test -1, 1, and 5. So if I use this line, which it doesn't really matter if you use this line or this line, both of those would work. So if I plug in -5, I have negative, if I go by the top green star, that might be a little bit easier. I have a -5 on the outside. 25 minus 16 is positive. Negative times a positive is going to be a negative. If I plug in the -1, I have a negative on the outside and a negative on the inside. When I multiply those, I'm going to get a positive. If I plug in a 1, I have a positive on the outside and negative on the inside. Plug in the 5, positive on the outside, positive on the inside. So this graph is going to be looking like that. If I'm looking where this is less than 0, that is where my graph is negative. So I want to name all the areas where my graph is below the x-axis. So from -4 to the left, we are below the x-axis. You can write that as x is less than -4, or you can write that as -infinity to -4. And then x is also negative from 0 to 4, or you can write that using interval notation. So you can write those in either way. And that would be your solution to the question. Those are the places where it's negative. And again, it's helpful to know where your graph is negative or positive. It helps to give you a good idea of how to actually go through and sketch that out. So there is a concept summary in your book on page 167. Again, you can get to that in the electronic version of the textbook. Or if you signed out a print copy of the textbook, you can look in that as well. Please go back through and watch this video. Again, this and 3-6 are very, very closely related. 3-6 will give you even more tips for how to come up with some ways to solve some of these polynomial functions. So go back, rewatch this, and reach out to me if you have any questions at all.